So today, let's talk about cross products. Cross product, also known as vector product, is a form of vector multiplication that results in a vector. Recall from our previous video that dot products multiply the parallel components of vectors together and result in a scalar. Cross products multiply the perpendicular components of vectors together and result in a vector. Why would we want to do that? Let's begin by taking a look at the motivation for defining cross product in Cartesian coordinates. Imagine some vector A that points along the x direction. Vector A equals A x hat, and another vector B that points only in the y direction. Vector B equals B y hat. Now, the dot product of vector A and B is 0. In general, the dot product of perpendicular vectors will always be 0. Taking the dot product of vectors A and B does not give insight into how the vectors are oriented. If there was a vector z in the z direction, vector c equals c z hat, the dot product between vectors b and c will also be 0. The orientation of vectors a and b is different than the orientation of vectors b and c. Vectors a and b lay parallel to the xy plane, while vectors b and c are parallel to the yz plane. We could not infer that from only seeing the results of these dot products. The motivation for defining cross product is to have a vector operation that retains some information about the original orientation of our vectors. This can be done if cross product results in a new vector that is perpendicular to both of the original vectors and the plane they are in. A vector that's perpendicular to a plane is referred to as a normal vector. Taking the cross product of vector A crossed with vector B results in a normal vector to the plane vectors A and B lie in. Walking through this, vector A crossed with vector B equals A x hat cross B y hat. Their cross product should be in a direction perpendicular to both x hat and y hat. A direction that is perpendicular to both x hat and y hat is z hat. The cross product of vector A crossed with vector B equals AB z hat, where AB is the multiplication of the vector magnitudes and z hat points in the direction perpendicular to both vectors A and B. If we saw the cross product of two vectors is in z hat, that tells us that z hat is normal to the plane those two vectors lie in. Cross product is defined such that the result of crossing two directional unit vectors is the remaining unit vector. The overall definition of cross product is x hat cross y hat equals z hat, y hat cross z hat equals x hat, and z hat cross x hat equals y hat. However, order matters. Y hat cross x hat is negative z hat, z hat cross y hat is negative x hat, and x hat cross z hat is negative y hat. Flipping the order of the cross product flips the resulting sign. For most of your math education, you are used to numbers commuting, as in A multiplied by B equals B multiplied by A. However, this is not true when it comes to vectors and cross products. Vector A cross with vector B equals the negative of vector B cross with vector A. This is referred to as anti-commuting. The cross product between a unit vector with itself is 0. X hat cross x hat is 0, y hat cross y hat is 0, and z hat cross z hat equals 0. One trick to remember the cross product definitions is by drawing out this diagram. If you are doing cross products, such as x hat cross y hat, you start at x and follow the arrows to y, which results in positive z. However, if you do y hat cross x hat, you start at y and go to x against the arrows. That's a negative z because you went against the arrows. Let's do our example with numbers. If d vector equals 2x hat plus 3y hat and vector e equals 5y hat plus 7z hat, let's find the cross product of vector d crossed with vector e. vector d crossed with vector e equals the quantity 2x hat plus 3y hat crossed with the quantity 5y hat plus 7z hat. We need to first distribute the cross product to get 2x hat cross the quantity 5y hat plus 7z hat plus 3y hat cross with the quantity 5y hat plus 7z hat. Distributing the 2x hat, we get 2x hat cross 5y hat plus 2x hat cross 7z hat. Now we can multiply the numbers and then take the cross products of the directions. 2 multiplied by 5, x hat cross y hat plus 2 multiplied by 7, x hat cross z hat. This equals 10z hat plus 14 x hat cross z hat, which is negative y hat. Now let's distribute the 3y hat. 3y hat cross the quantity 5y hat plus 7z hat equals 15y hat cross y hat plus 21y hat cross z hat. The cross product of y hat with itself is 0. And the cross product of y hat cross z hat is positive x hat. Vector d cross vector e equals 10z hat plus 14 negative y hat plus 15 multiplied by 0 plus 21x hat. Let's call this vector f. Vector f equals vectors d cross e equals 21x hat minus 14y hat plus 10z hat. This new vector f should be perpendicular to both vectors d and e. How do we check if two vectors are perpendicular? We see if their dot product is 0. Let's check this. Remember, dot product multiplies the parallel components of vectors together. Vector d dotted with vector f equals 2 multiplied by 21 minus 3 multiplied by 14 equals 0. Vector e dotted with vector f equals 5 multiplied by negative 14 plus 7 multiplied by 10, which is 0. We just confirmed that vector f, the cross product of vectors d and e, is perpendicular to both vectors d and e. Let's take a look at the cross product of two parallel vectors. Because cross product multiplies the perpendicular components of vectors together, two parallel vectors should have a cross product of 0. Let's check this. Take vector g to equal 1 x hat minus 3 y hat and vector h to equal 2 vector g. Remember, parallel vectors can be expressed as scalar multiples of each other. Now, we are going to check to see if the cross product of vectors g and h is 0. Vector g cross vector h equals 1 multiplied by negative 6 x hat cross y hat minus 3 multiplied by 2 y hat cross x hat, which equals negative 6 z hat minus 6 negative z hat, which adds up to 0. It worked. It can be shown the cross product of any two parallel vectors is always 0. You can see that the cross product between two vectors depends on the angle between the two vectors. If two vectors are at an angle of 90 degrees, their cross product is maximized. And if two vectors are at an angle of 0 degrees to each other, when they're parallel, their cross product is 0. Whenever we see an angle dependence in physics, that's a clue that a trig function is probably going to pop up. It turns out that the magnitude of the cross product between any two vectors is equal to the magnitude of the two vectors multiplied together multiplied by a trig function of the angle between the two vectors. What trig function do you think we should use? Well, when two vectors are perpendicular to each other, the cross product is maximized, and when two vectors are at an angle of 0 degrees to each other, when they're parallel, their cross product is 0. Which trig function is maximized at 90 degrees and equal to 0 at 0 degrees? Sine. We can write that the magnitude of the cross product between any two vectors a and b is equal to the magnitude of a multiplied by the magnitude of b multiplied by sine of theta. You can recover that the magnitude of a cross product depends on sine by going through these limiting cases. So where does cross product show up in physics? All over the place. from torque and angular momentum to magnetic forces and magnetic fields. But we're going to focus on torque here. Torque is the application of some force to an object a radial distance away from an axis of rotation that results in rotational acceleration, which, all being said, is a complicated way to describe how you open the door. In torque, we have two vectors, a vector representing the applied force and a radius vector that points from the axis of rotation to the spot the force is applied. Let's take a look at a door. A door has hinges at one end, fixing that end and allowing for only rotational motion. The force vector points into the door in the direction the force is applied. The radius vector starts at the hinges and points to where the force is applied. Torque is defined as the cross product radius cross force. Suppose we have a force of 10 newtons applied to a door 0.25 meters away from the hinges. Let's find the torque. First, we need to define a coordinate system. Let's define the origin at the axis of rotation in the middle of the door. The z-axis points upwards along the hinges, the x-axis points away from the hinges along the door's initial position, and the y-axis is perpendicular to both of the other axes. This means the radius vector is 0.25 meters x hat and the force vector is 10 newtons y hat. Now, calculate the torque. Torque equals radius cross force, which is 0.25 meters x hat cross 10 newtons y hat, which gets 2.5 newton meters z hat. What does this say about the direction of the door's angular acceleration? Looking from above, we intuitively know that when we push the door like this, it will spin counterclockwise. What if we were looking from below? The angular acceleration is now clockwise in this perspective. Oh boy, this can get confusing. The torque vector should provide us with information to infer the direction of angular acceleration in our coordinate system. The sign of a torque vector tells us information about direction of angular acceleration. In translational motion, the sign of a vector indicated if the vector was pointing right or left, up or down, or into or out of the page. The sign of rotational direction tells us counterclockwise or clockwise with respect to our axis normal to the plane of rotation. To figure out the rotational direction, we need to look at the plane of rotation from the perspective of the positive axis the torque vector is pointing along. We have torque equal to 2.5 newton meters z hat. This means the xy plane is the plane of rotation. We define the z-axis to point up from the ground along the hinges. We need to look at the plane of rotation from above. From here, a positive value represents counterclockwise movement about the axis of rotation, and a negative sign indicates clockwise movement about that axis. So our torque of 2.5 newton meters z hat means this door will rotate counterclockwise about the positive z-axis. Remember, the order of cross product matters. Torque is defined as radius cross force, not force cross radius. If we did force cross radius, that would result in the opposite sign of the torque, negative 2.5 newton meters z hat. Which, with our sign convention, means clockwise rotation about the z-axis. We can see the opposite is happening in this case. So remember, be careful with the order you cross vectors. Torque equals radius cross force, not force cross radius. If you forget, use your physical intuition to reason which way the door should rotate to determine the sign. If we flip the direction the force is applied, our new force is negative 10 newtons y hat. This will cause clockwise rotation of the door. The torque now equals 0.25 meters x hat cross negative 10 newtons y hat, which equals negative 2.5 newton meters z hat, where the negative sign indicates clockwise rotation about the z-axis, which is what happens when the direction of the force flips. Let's see how angle between the force and the door fits in. We will keep force at a fixed magnitude, but decrease the angle between the force and the door from 90 degrees. There is now both a component of the force parallel to and perpendicular to the door. Any 2D vector can be expressed in terms of its x and y components. We can define the x and y components of the force in terms of the force's magnitude using trig. Let's draw a triangle of the force vector to the side. The x component of the force is parallel to the door in the negative x direction and depends on the cosine of theta. The y component of the force is perpendicular to the door in the negative y direction and depends on sine of theta. The x component of the force is negative the magnitude of the force cosine theta, and the y component of the force is the negative magnitude of the force sine theta. When we take the cross product to find the torque, we find torque only depends on the component of the force perpendicular to the door, which is the y component in this example. Torque equals R multiplied by the y component of the force, x hat cross y hat, equals R y component of the force, z hat, which is negative R magnitude of the force, sine theta z hat. We can find the magnitude of the torque to be the magnitude of negative radius force sine theta z hat. We call the magnitude of a unit vector as 1, so the magnitude of the torque is radius force sine theta. Now, as theta goes to 0, the magnitude of the torque decreases. When theta is equal to 0, we can see that the force vector is now parallel to the radius vector, yielding 0 torque. If we try to apply a force parallel to a door, you can see that the door does not rotate. There is indeed 0 torque. Well, it's time for the review. No video is complete without one. Just like no book is good unless the author tells you what it all means in the very last chapter. We learned that cross product is a form of vector multiplication that's also called vector product because it results in a vector. Cross products multiply the perpendicular components of vectors together to give a new vector that is normal to the plane that both of the original vectors were in. Cross product is defined to be x hat cross y hat equals z hat, y hat cross z hat equals x hat, and z hat cross x hat is y hat. But be careful, the order of cross product matters. If you flip the direction of your cross product, you flip the sign of your cross product, such as y hat cross x hat is negative z hat. Cross products are anti-commuting. The cross product of parallel vectors is always 0. Finally, we looked at an example of cross product used in physics. Torque is equal to radius cross force, and saw how the sign of torque indicates the direction of angular acceleration being counterclockwise or clockwise in the plane with respect to the axis the torque is pointing in. Guess this is a good time to end the video. You might get cross with me if I make the video much longer.